Kerm. I'm a professor of inequality and social policy at the University of Luxembourg and at the Luxembourg Institute of Socioeconomic Research. So under normal circumstances, I would have been lecturing at the LISSY summer workshop about various aspects of analysis of income and wealth distributions using LISSY and LWS data. Well, in the absence of that, let's have a few video tutorials instead. And in this short tutorial, I want to talk you through handling loose multiply imputed datasets. It's not very complicated, but I think it's fairly important because it's actually really easy to get things wrong. So I recommend you first watch Piotr Paradowski's video on the structure of loose data, and then follow me through this video tutorial on how to work with loose multiply imputed datasets. So what's specific about multiple imputations is that, well, every missing data is not replaced by one imputation, but by multiple plausible values. Multiple plausible values. And typically this is done using some form of stochastic imputation. There's a prediction, an expectation of the missing value, and there's residual added to that. And the idea is that, you want to preserve the variability in the data. You want to preserve, to have imputation that reflect the uncertainty and the randomness in the data. Okay, so what happens practically is that you receive as a user, a dataset, not just one dataset. Okay? You don't get that dataset which has two variables and say 3 observations with missing data and fit values. Okay, now what you get is several replications of the same data. So here 3, okay, 3 variables, 3 observations, but in those multiply imputed data you will get those missing values replaced by imputations. Okay, so this remains 2, 5, 1, etc. This is 2, 5, 1, this is 2, 5, 1. Okay, but the missing values here are going to be replaced by multiple plausible values. So let's say this one is 2, and here it's 3, and here it's, say, 2 again, and this one has a lot more uncertainty, so maybe it's 1, maybe it's 9, and maybe it's 2. Okay, so we've got 5 multiply imputed datasets. And of course, those don't have holes anymore. Alright. Okay, so if you're a loose user and you are using the US SCF, for example, well, once you start and open your US, let's say 16H file, what you actually get is this. You've got a long dataset where actually 5 multiply imputed datasets are stacked into one big file. Okay, and this one is not there. Okay, one really long dataset. So, how are we going to use that? Okay, well, let's first look at how not to use that. There's 2 big mistakes that you want to avoid, and the first one is the catch. The first one is to actually treat that whole big dataset as one large sample. And that's obviously wrong, because the duplicated observations are not 2 randomly sampled observations from your population, they're just copies of each other. So if you think of those which are not imputed at all, they're just copied 5 times. So it's not 5 different people in the population. And so you're underestimating the sampling variability, obviously, and because you're stacking 5 datasets, well, your sample size looks much bigger than it really is, so whatever calculation of the variance and confidence interval is going to be very wrong. Okay, so don't do that, and that's the catch. I mean, because the dataset is provided as one large file with 5 replications stacked on top of each other, it's very easy to fall prey to that mistake. So be aware, don't do that. Okay. Second bad idea, you realize that what you have is actually 5 datasets stacked on top of each other. The second bad idea is to actually combine it by taking the average across the 5 implications in the all observations and variables. Don't do that. If you do that, you lose entirely the benefit of this stochastic imputation. So you're actually imputing missing data to their averages, so you lose the benefit of stochastic imputation, and you underestimate the real variability in the data. So if you're doing, for example, inequality calculation, that's going to be very wrong. So what should we do? Well, the first option is the easy one, or the lazy one. It's simply to discard, just to work with one of the 5 datasets. Okay, not so great, but it's not all that bad solution, because the inference is perfectly valid. You just don't exploit the multiple imputation to the full. But looking at your estimation within one specific dataset is fine. Just keep the first one if you like, or keep the fourth one if you like, whatever. They're all just perfectly equivalent to each other, different but equivalent, they're equally valid, and you run your entire analysis on just one of the implicates. Of course, once you've done that, well, you probably want to go the extra mile and assess the sensitivity of your results to having picked up another one. So why not just repeat your analysis on all available datasets and just have a look at how robust your conclusions are to using a different dataset. Yeah, that's probably a very good idea, just to convince yourself that what you get is not just what comes from the imputations. But now that you've done that, you probably want to go one extra mile again and exploit the multiple imputation to the full. Well, the idea is that you will run your analysis on each of the 5 implicates, and you're going to get the point estimate as the average of the estimate you get in the 5 estimations. Alright, so QM would be whatever measure you're interested in. It could be an inequality measure, or let's say a regression coefficient estimated on the mth implicate. Okay, that's QM. And the point estimate is the average of that across the 5. Very easy. Now, the slightly more complicated measure is the estimate of the variance, from which you're going to derive standard errors, confidence intervals, etc. And for that, it's very common to use the so-called Rubin's combination rule, and that's the following. So it's a combination of the standard errors that you'd estimate within each of the 5 implicates. Okay, you run your regression, you've got the coefficient and the standard errors and the variance. Okay, take the average of that across the 5 implicates. That's the within implicate variance. But you need to add to that the variance that you observe across implicates. And that's reflected by B. And B here is simply the variance of the QM of the 5 QM values. So if there's a lot of imputation and it has a big impact on your estimate, the 5 values are going to be very different and B might be large. But if actually imputation is very limited and doesn't make a whole lot of difference, it's very likely that this is going to be a very small number. But whatever, that's something you need to check afterwards. And this is the way you'd estimate the standard error, the variance of your estimates. Okay? And having that, you can derive confidence intervals and tests, etc., etc. Okay, I recommend you check this book where it's all very clearly explained. Of course, you're not going to do those calculations manually, so your favorite statistical software package will do the calculations for you. Okay, it's available in R, in SPSS, in SAS, and in Stata. I'm going to show you examples in Stata. So, the process is really simple. You load the entire loose dataset, so the 5 stacked dataset. You then declare, so you tell Stata, watch out, this is not just one big dataset, it's 5 multiple imputations. Okay, that's the MI set and MI register. I'm going to show you examples in a minute. And then once you've declared your data to be a set of multiple imputed datasets, you will prefix your estimation command by MIEstimate to tell Stata to actually run the estimation 5 times and combine the standard errors using Rubin's combination. Okay, for example, you're going to do MIEstimate regress whatever you want to do. Okay, there's one catch, however, is that, well, Stata and most other software would expect to have the unimputed data available as well. What Stata would call M0, the unimputed data with the holes. Whereas loose actually only contains the fully imputed data. So what you're going to have to do is we'll have to recreate the original unimputed dataset and add it to, okay, sorry, to scale. We've got our 5 multiply imputed datasets. We're going to have to create number 0 and add it to those so that we can use it as MI, suite of MI comments. So let's look how to do that. Okay, so now let's look at an example. I fired LISSY here on an interface, and I am going to work with loose data, and here we are going to use upload here some script which I have prepared before. Okay, so what's in this script? First thing first, we are using the US data 2016, the household file, okay, and we're going to tabulate INUM. So INUM is the identifier for implicates. We're going to see there's 5 different INUMs with exactly the same number of observations. A little catch which you may not be, don't worry about it. What happens here is that across those 5 implicates in that particular dataset, the household weight is actually varying with the implicate, which means that some of the calibration is using imputed variables. Probably not something you want to worry about, so here we're going to ignore that variation in the weight, and we are going to replace the value of HPOP-WGT by the value of HPOP-WGT in the first implicate. So instead you do that by saying sort, so by HID, sorted by INUM, so we're going to have blocks of HIDs, and within an HID the 5 replicates, and here say, okay, use the first value of the household weight and apply it to all values. Okay, it's a minor issue, you probably can safely ignore that. Alright, how can we now do the analysis? Well, the easy way is say, okay, let's keep just one of the 5 implicates and run our analysis. And our analysis is simply calculating the average of A and W, so a measure of net worth, total net worth, and the Gini coefficient of A and W, so inequality in this net worth variable. Keep non-positive means keep the zeros and the negatives. But because we want to have to do proper inference, I'm using this SVY setup here, so I say SVY set, use HPOP-WGT as sampling weight variable, and I'm specifying HID as primary sampling unit. That's a simplification, but that's not very important. And then I prefix all those commands by SVY so that Zeta will apply those weights in the estimation. Alright, so far so good. We can stop here. But although we could stop here, it's probably a good idea to go the extra mile and see do these things vary a lot if I work with a different implicate. So let's select 2 now and run the same analysis. Notice I do that within the preserve and restore. So I have the 5 implicates, preserve, keep 1, and then restore. I get back to the 5 implicates, preserve, keep just 2. Okay, so only 2 is in memory, restore, bring back the 5 implicates, etc. So here we manually select 1, 2, 3, 5, 1, 2, 3, 4, 5, sorry, but you probably want to put that in a data loop if you're familiar with coding loops in your do files. So you would have a loop that goes from 1 to 5 and use so SVY set as before, and here I'm using a slightly different syntax. I'm running that command only if INUM is equal to 1, 2, 3, 4, 5. That's in the loop. Right. And here I'm actually storing the estimate within each pass through the loop and looking at the average. Okay. So practically that's just for the example and to show that the consistency of that this is what we get below. In practice you probably want to use state as MI prefix. So recall that to use MI prefix we first need to create this unimputed implicate, so M0. So it's a bit of manipulation, but that's fairly easy and that will always be the same. Okay, how are we going to create this? Well, the key thing is first to identify which values of net worth is actually imputed and which is not imputed. And you'll realize quickly that a lot of those observations are imputed. Why? Well, simply because net worth is composed of very many components, And it can be that if any one of those components has been imputed, well, the overall is considered to have been imputed. Alright? So, how do I identify imputed from non-imputed? That's very simple. We look at the standard deviation of the values of A and W for a particular household. So, the standard deviation across the 5 implicates. If it's constant across the 5 implicates, so the standard deviation is 0, then we'll conclude that this observation has not been imputed. If, on the other hand, we observe that the value of A and W varies for that observation across the 5 implicates, so the standard deviation is above, is more than 0, then we'll conclude that this observation has actually been imputed. Okay, so that's how we set this up. So we create the standard deviation of A and W within HID, so for each household. And if that standard deviation is positive, this is equal to 1, and so we say we create a tag, a flag variable called imputed equal to 1. If the standard deviation of net worth across implicates is greater than 1 for that household. And it's going to be 0 otherwise. Okay, now we have a variable which identifies which observations of A and W have been imputed, which haven't. We no need to use that to create this unimputed dataset. So how do we do it? Well, we're first going to use that expand command, and expand is very simply duplicating observations. So here I'm using expand 2, so duplication, if inum is equal to 1. So I'm duplicating implicate number 1. And we create this original variable which is going to be 0 for the clones and 1 for the origin. Then, okay, we are going to recode inum, to reset inum to 0 for the clones. So inum is equal to 1, but original 0. So that's the clone that we just created. So we call it implicate 0. And for that clone, we are going to replace all values of A and W to missing if they are tagged as having been imputed. And there we are. That's all. We now have 6 implicates stacked on top of each other, where implicate number 0 is unimputed. Now that we have that in memory, we tell Stata that, well, that's an MI setup. So here we're going to call it MI import flong. Flong is that particular specification where data sets are stacked on top of each other. There are different ways to store those data. Just look at the Stata documentation. But here in the context of loose, that's always what you're going to use. Okay, MI import flong. I'm telling which is this inum variable, which variable identifies the implicate. In this context, inum, which is the individual identifier, that's HID. And here will appear the list of variables which have been imputed. In this context, simple example, A and W. Alright, so we declare data to be multiply imputed. Let's also declare the data to be SBY set. Okay, survey data, so now it's MI SBY set. We declare the weight variable and the primary sampling unit, which here again we're going to assume is simply the household. And that's all there is. We can now prefix all our estimation commands by MI estimate, the estimation command, and Stata will automatically do the combination across the 5 implicates and use Rubin's combination rule to get the standard errors in the tests. And that's all there is. Now, all the rest, there's more you can do. You may want to, using these noisily var table sub-options of MI estimate, you can also look at the value within each implicate. You can use MI execute to actually run the command on a specific implicate if that's of any use. Here it's going to execute that command only for implicate number 1 or implicate 0 and 1. And with this notation separation using semicolon, you can have multiple commands being executed here. That's all stuff you may want to check in the Stata manuals. I will not spend more time looking into that. That can also work with non-estimation commands. So by default, MI estimate runs whenever for Stata estimation commands, so returning results in EB. You can do a bit of tweaking to actually run it on any sort of commands. There's an example here that you may want to look for yourself. And you can also combine multiple imputation setup with the replication weights. So I'm not going to look into that in this video. There's another video where we look specifically at using replication weights, and we're going to look at those examples again in that video. Okay, so let's run it through LISSY and let's see what we get. Right, so just to confirm, we're using US 2016, and indeed we have 5 replications of the same file. So our data is 6,248 households. It's not 31,000 different American households, right? So that's the relevant sample size, 6,000. Okay, so we're going to look at adjusted disposable net worth, which is an aggregate of very many different components, but as we can see here, there's actually no missing data in that period, which suggests, well, that this has been imputed. Okay, it's, well, let's not look at the numbers. We've done that little tweak to fix, to use the household weight of the first implicate in all implicates, so that works. Let's not pay too much attention to that. Okay, so let's first do our grand analysis the easy way, which is keep just one of the implicates. I'm using one. I could have equally used any of the implicates. So keep just one of them. I SVY set the data, and I run my mean and my inequality, and we find that the average net worth is $666,000, and the Gini coefficient is a large 0.86866 approximately. Okay, there it is. We could stop here, and we've got perfectly valid inference. Of course, we want to go the extra mile and try and check the sensitivity of those numbers to using a different implicate. And what we find is, well, on implicate number 2, the mean is actually somewhat larger, and the Gini coefficient is slightly lower, but actually pretty close. What about implicate number 3? Well, still a bit larger, so we sort of get some variation across implicates, and we've got yet another value for the Gini coefficient, which is not all that. Okay, we could have done that in a loop here, and you'll want to look for yourself. You could run the file on your end and check that it runs. That's doing the same thing on the 5 implicates in a loop, okay, and storing the average value. So you see the average here is kind of significantly larger than, well, not in a statistical sense, larger than what we find in implicate number 1. Okay, and the Gini is not so very different. But let's now use Stata's MI prefix to do things properly. Okay, so recall, first thing we need to do is create this unimputed data. So there we are, we've got this egen command, we create this imputed value. Let's check how many of the values that are imputed, and wow, so you see, that's a very large number. So only 11% of the observations are actually constant across the 5 implicates. And 88%, actually the value of 88% of observations have a value for adjusted net worth that varies across implicates. The reason for that is obviously that this is a combination of very many small components, and it might be that just one is actually imputed. Okay, now the little tweak, we expand, we create those artificial item 0, that's all running. We declare data to be f-long, it does run. We declare mi set, it does run. I just check that it's running fine, so yes, it's indeed mi set long, and Stata has found 5 implicates. It doesn't count the 0, since 0 is there. And there we are. So what do we get with mi estimate prefix? We've got that. We've got an output that pretty much looks like the output we had when using just one implicate. The point estimate is this 675, which is the average across the 5 implicates, and we have an estimate of the standard error that takes into account. That's using Rubin's combination rule. That takes into account the estimation of the mean within an implicate and the variation in the mean that's due to the fact that that's related to the imputation. So that's the variability. It combines the variability of across imputations. Okay, so that's what you get here. That's giving you the fraction of the variance that's related to the imputation, and that's about 8%. So you can interpret that as saying that about 8% of the total variance is due to the imputation variance, and therefore 92% is actually sampling variance that's within each of the implicates. Gini coefficient, well, same thing. We've got a Gini coefficient, we've got standard errors, a confidence interval, and all those numbers actually take into account the variability that's due to imputation and the inherent standard errors due to sampling variability within each of the implicates. So that's easy, and that's making full use of the multiple imputation. Okay, you may want to stop here. All the rest is just looking at the gory detail. So if we have those extra options, we just repeat the same analysis, but now Stata is going to show the output for each of the separate. We've got the results for that we know the 666000 value for the average. That's what you get in implicate number 1, number 2, number 3, and I'll let you check all that for yourself, how it runs. But as you see, it's really easy. The point is you need to set up to create this M0, tells data that your data is multiply imputed, and then use the MI estimate prefix to run your analysis. Of course, there's a lot more than what I've just shown in terms of using MI estimate, and you'll have to spend some time in the Stata manuals, but that's important to do that if you want to make full use of the multiple imputation in loose. So there it is. So as I said, this file is going to be available for download on the LISSY website, so you can run it for yourself, and I encourage you to do that. So I hope this was helpful.